Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
Welcome to this explainer. Look, if staring at a dense matrix has ever just completely given you a headache, let's go ahead and reset our expectations together. We aren't here to crunch endless numbers today. No way. Instead, we're going to explore the dense mathematics of abstract linear algebra as this thrilling architectural blueprint. It's literally the foundation for building an entire mathematical universe, and we are going to explore exactly how it's constructed step by step.
Okay, let's dive right into this. Here is our roadmap for today. We'll start with vectors and linear transformations, then move to dual spaces and functionals, check out spectral theory, canonical forms, and explore the geometry of inner products. After that, we'll do a quick comparison of textbook pedagogical approaches, and finally, wrap it all up with the unified mathematical framework.
So, starting us off. Part 1. Vectors and linear transformations. You can really think of an abstract vector space as the empty stage where our whole mathematical universe is going to take place. I mean, before the actors can perform, you need a stage, right? By definition, it's a set equipped with vector addition and scalar multiplication over a field, usually the real or complex numbers. And what's super fascinating here is how this actually evolved. It started out just as concrete methods for solving basic systems of linear equations, but eventually mathematicians realized these specific solutions formed a much grander, abstract stage of geometric linear spaces. So once we have our stage, we really need to figure out how to build on it. And that brings us to Theorem 1.1, the characterization of direct sums. The absolutely crucial point here is that a space V is a direct sum of subspaces U and W if and only if V equals U plus W and their intersection is exactly the zero vector. What does that mean structurally? Well, it means that every single vector in our entire space can be written uniquely as a combination of a piece from U and a piece from W. It creates this incredibly solid structural foundation where components just don't overlap or interfere with each other, which is perfect before we start introducing any motion. And hey, speaking of motion, let's introduce the actors on our stage, linear transformations. Theorem 2.1, the rank nullity theorem, is honestly one of the most beautiful balancing acts in all of math. It tells us that the dimension of your starting space, V, is equal to the dimension of the null space plus the dimension of the range. And this brilliantly illustrates a kind of cosmic conservation law in our mathematical universe. Basically, a linear transformation T takes your space and it either crushes parts of it down to zero, that's the null space, the destroyed part, or projects it into a new space, that's the range, the created part. The total dimension you start with, it's always perfectly preserved.
Moving right along to Part 2, dual spaces and functionals.
Okay, so now that we've got our stage and our actors, let's introduce the mathematical observers. This observer space is called the dual space, which we denote as V star. It's basically the space of all linear functionals from our vector space V back to our scalar field F. Instead of moving vectors around, these functionals act as measurement tools, scalar evaluators. You feed them a vector and boom, they spit out a number. And what is truly elegant about this is Theorem 3.1. It proves that for any finite dimensional vector space, there's a unique dual basis. That means the dimension of the vector space perfectly matches the dimension of its dual space. The stage and the observers of the stage are literally perfectly symmetric in size.
Next up, Part 3, spectral theory canonical forms.
So if linear transformations are our actors, you can think of spectral theory as the script that actually dictates their behavior. To read the script, we look for patterns using T-invariant subspaces. An invariant subspace is essentially a pocket of our space where, if you apply your linear transformation T to it, the output stays completely trapped inside that exact same pocket. Finding these invariant subspaces and generalized eigenspaces is incredibly powerful. Why? Because it lets us take these wildly complex operators and break them down into much smaller, isolated, and totally manageable fundamental building blocks. Now, this modularity really reaches its peak with the primary decomposition theorem. It tells us that if we let the minimal polynomial factor into distinct monic primes, our space just perfectly fragments into T-invariant chunks. We're literally treating our vector space as a module over a polynomial ring here. By taking the minimal polynomial, which is that core equation that uniquely annihilates our operator, and breaking it down into prime factors, this theorem perfectly modulizes our entire space into a direct sum of independent invariant pieces. It's like taking apart a giant puzzle perfectly. And this brings us to a really fascinating contrast between the two ultimate canonical forms, basically the purest, most distilled ways to represent our operators. On one hand, you have the rational canonical form. This uses cyclic decomposition to give us block-diagonal companion matrices based on invariant factors. And the really great thing about that is it works over any field. But on the other hand, if we upgrade to an algebraically closed field, something like the complex numbers, we get the incredibly elegant Jordan canonical form. That's where those polynomials factor all the way down into these beautiful diagonal Jordan blocks.
All right, on to part 4, geometry of inner products.
So up until this exact moment, our mathematical universe has been purely structural. It's totally lacked any actual physical measurement. Well, we solve that by defining an inner product space. We equip our vector space with a positive definite Hermitian form, and this strictly requires conjugate symmetry, linearity, and positive definiteness. Now you might be wondering, why do we even care about these super strict rules? Well, because this specific definition is what finally grants our abstract universe the physical concepts of length, angles, and orthogonality. It even gives us the famous Cauchy-Schwarz inequality, which ensures that the relationships between our vectors behave in a way that is physically intuitive.
And because we have orthogonality now, we can actually build the perfect grid for our universe using the Gram-Schmidt orthogonalization process. You can think of it kind of like carving a pristine, perfect cube out of a jagged rock. Step 1, you set a baseline vector. Step 2, you iteratively subtract the projections of your remaining vectors. You're essentially stripping away any overlapping messy directions. And step 3, you normalize each new vector to a length of exactly 1. It's this highly practical, step-by-step construction that turns any messy, chaotic basis into a pristine, orthonormal grid. Which brings us to the absolute climax of our operator theory, the complex spectral theorem. This theorem states that an operator T is normal, meaning it perfectly commutes with its own adjoint, acting symmetrically with its transpose, if and only if the space has an orthonormal basis consisting entirely of eigenvectors of T. This is huge. I mean, it beautifully unifies algebra and geometry, essentially proving that the most structurally sound operators are exactly the ones that can perfectly align with a geometrically pristine, orthonormal grid of their own making.
Let's shift gears a bit for part 5, comparing textbook pedagogical approaches.
So let's introduce a bit of a meta-narrative twist here. If we step back and look at the builders, the legendary mathematicians and educators who construct these frameworks to teach us, we see some starkly different philosophies. For example, Sheldon Axler champions an operator-theoretic approach that is famously determinate-free, focusing really heavily on invariant subspaces. Contrast that with Hoffman and Kuhns. They take an axiomatic, modular theory approach using polynomials. Then you've got Gilbert Strang, who approaches the whole thing through matrix factorization, geometric projection, and singular value decomposition. And finally, Shea offers a highly constructive computational geometric framework. So it's the exact same mathematical universe, but completely different blueprints for building it in your mind. Finally, part 6, the unified mathematical framework. We've looked at the parts, the operators, the geometry, and even the teaching methods. Now, tying this entire blueprint together yields 4 really core insights. First, dimensional invariance. The rank nullity theorem and direct sums strictly govern the conservation of our space. Second, canonical operator representations, proving complex operators can always be distilled down to their essence. Third, the module structure of endomorphisms, which links our linear maps directly to the deep theory of principal ideal domains. And fourth, geometric operator theory, unifying algebraic eigenvectors with orthonormal geometry. These 4 pillars, they aren't just abstract ideas, they literally form the bedrock for quantum mechanics, differential geometry, and the numerical linear algebra that powers all of modern computer science.
So I want to leave you with this final, somewhat provocative thought. Every search engine, every artificial intelligence model, every quantum computing breakthrough relies on the precise geometry and structure we just explored. How does your newfound perspective on these abstract mathematical foundations change how you view the hidden linear algebra blueprint structuring our entire digital reality? It's pretty wild to think about. Thank you so much for exploring this blueprint with me today, and definitely keep questioning the structure behind the world around you.
Like what you shared.
This website makes learning so easy. I found all my resources here.
Noir plasma chrome bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.